high-performance computing is fundamental to their work. It's a very large market, of course. I believe this is going to be 100% accelerated computing in the near future. CSPs, cloud service providers, using high-performance computers in order to do deep learning training their neural networks. And then when they are done training their neural networks, they put it up into the hyperscale cloud so that they could run queries against their data center from billions and billions of users. Each one of those queries are likely in the future to represent several deep learning networks. The public cloud. I just mentioned earlier, Microsoft just put up VOLTA into Azure. Incredible opportunity for researchers all over the world. And the reason for that is because they all need high-performance computers now, and deep learning researchers particularly, and for the first time, they can access the most advanced computers in the world without having to build it. And not only that, it's only $3 an hour. For researchers, for startups who rather take their hundreds of millions of dollars of investment and use it to hire engineers and hire people instead of building infrastructure, they can now go to the cloud and get their company started. The public cloud is going to be a very large market for us. But I think the largest market will ultimately be the industries. And the reason for that is this. Whether you're in healthcare or finance or manufacturing, logistics, the opportunity to apply deep learning and AI for the very first time allows us to solve what are previously unsolvable problems. I'm going to show you one example of the work that we're doing in using artificial intelligence for self-driving cars. But industry after industry after industry, AI and deep learning has made it possible for us to the first time think about solving these unsolvable problems. And then lastly, using high-performance computing inside the enterprises, whether it's virtualized all of the computer graphics, or one of these days, there'll be an AI inside Nvidia looking at all the business transactions that we're doing and essentially writing another AI that turns Nvidia into an AI. I'm super excited about that day. And so all of this are GPU accelerated today. So many exciting applications that define each one of these industries. And as I mentioned earlier, it's about the processor, it's about the architecture, about the system, but in the final analysis, it's really about the software stack. It's about CUDA, it's about cuDNN. It's about our AI SDK, which includes Nickel and TensorRT. The fact that we worked so closely with each and every one of the framework developers to accelerate their framework. And of course, one of the most important things we've done recently called the Nvidia GPU Cloud, a registry that contains these really super complicated software stacks, and we put it in the cloud for you to run the software stack everywhere. Today I want to talk about several things. I want to give you an update, of course, of our company, but I'd like to talk to you about our perspective on architecting modern data centers. How do you think about this really complicated problem? I'll give you some early reports of how deep learning has come to HPC and how exciting that is. The results are just going to be miraculous. And then lastly, I want to talk about software. High-performance computing is complicated, as you know. High-performance computing is large-scale computation, processing enormous amounts of data, creating enormous amounts of data on a very large scale. The software stack is complicated. The fields of science is diverse, and each one of their applications requires different acceleration layers. This aspect of accelerated computing is probably one of the least understood parts of accelerated computing, and yet it's the most important part of accelerated computing. The software stack of accelerated computing stacks of architectures is very different than writing a C program, compiling it to x86. So I want to talk to you about these three things. First, architecting modern data centers. Well, the problem is incredibly complex. And I challenged myself to put it all on one slide. And I think it largely is captured here. Imagine you have hundreds of different types of applications. And there are molecular dynamics, computational biology, fluid simulators, finite element analysis packages, all kinds of complicated applications, deep learning, all kinds of complicated architectures, applications. And it's connected on an architecture that has very high-speed storage, very high-speed networking, large number of computers breaking down a problem that each one of the computers is sharing its part. Okay? So high-performance computing is incredibly hard. The applications could be strong scaling, requires strong scaling, means the only way to make it faster is if all of the computers, all of the nodes are working very tightly together to solve one problem. Second, weak scaling, where even though they're not working that well together, you can solve the problem and solve larger and larger problems through greater and greater throughput, weak scaling. And then deep learning, which is a combination of a little bit of both. Excuse me, combination of a lot of both, deep learning. These three different types of characteristics of workload apply to a data center. The interesting about a data center, of course, like everything else in life, the 80-20 rule, a few of the applications consume the vast majority of the throughput or the workload, the runtime of that data center. And so the question is, as we think about accelerated computing and architecting this new data center, the question is, what kind of applications do we accelerate? And what percentage of the workload do they accelerate? And how fast does it speed up the parallel aspect of those applications, while not forgetting that Amdahl's law hangs over our head all the time? That we could accelerate the parallel computing component of our code infinitely, and yet the sequential part of the code that remains ultimately limits your speed up. And so today's data center, you have to be mindful about these things. What are the applications that you run? What aspect, what is the proportion of the total workload that it consumes? How do we accelerate those applications? Some of it requires strong scaling, some of it can benefit from weak scaling, and some of it is related to deep learning, this new application. How much parallel speed up do we provide? And what kind of remaining sequential percentage of the code is there, because we have to be mindful of Amdahl's law. And so the architecture of accelerated computing looks like this. It's basically these GPUs, these massively parallel GPUs that were designed for the domain of parallel applications. Let's ignore for a second all of the software layers that runs on top of it that's incredibly complicated. But let's just think about the processors themselves. Each one of these processors, in the case of VOLTA, 5,120 CUDA cores, all working in parallel. They're connected through this NVLink so that work can be shared, and each one of the parts of the work could be synchronized across the multiple GPUs so that we could scale for strong scaling. And we have this new instruction set called Tensor Core that allows us to speed up deep learning applications. And it's connected to the fastest possible, the best possible CPU you can find. And as a result, the CPU will continue to process the sequential code incredibly well and try its best to keep Amdahl's law from being the wall. And so accelerated computing has these characteristics. A CPU with strong core, massively parallel GPUs, connected with NVLink, and with accelerated capabilities. In the past, some of our accelerated functionalities were transcendentals, inverse square roots. And now, the accelerated features are much, much more complex, including tensor operations. And so accelerated computing architecture allows us to address many of the challenges inside a data center. Well, let me show it to you. So this is an AMBER application. It's a molecular mechanics force field solver. And so it's solving force fields of the molecules, biomolecules. And the reaction of the force fields on each other affects the other molecules around it. As a result, this is a strong scaling problem. And you can throw more and more processors at it, and more CPUs you spread the job over, connected over high-speed internet, high-speed interlinks like InfiniBand, you could split the work across more and more computer nodes. But as you see, the overhead of communications starts to overwhelm the processing to the point where each one of the computers are no longer that effective. And so strong scaling is not possible when you have these weak parallel computing nodes using CPUs. By porting Amber to CUDA, this is what you get. It's just an incredible result. By porting to CUDA with 4 V100s, and this is ISO cost. So this is one CPU and 4 GPUs compared against essentially 5 servers, 5 CPU servers, approximately ISO cost. And so the speed up is really quite spectacular. The benefit of strong scaling, the benefit of accelerated computing. But ultimately, the question is applications. I just mentioned one. There are so many applications, as I've mentioned. And this is really the advantage of CUDA, and this is the advantage of the architecture that NVIDIA has built. Over the course of the last 10 plus years, because of our commitment to CUDA, because of our relentless advancement of this architecture, as we continue to expand its reach, more and more applications ported. To this point, you've got a positive feedback system. Developers are jumping on this platform because it's now available everywhere. Platform providers are adopting VOLTA in a higher rate because there are more applications available. More applications available causes customers to embrace it at a higher rate. Customers embracing it at a higher rate causes developers to jump on it because they realize the benefit of the platform as well as the reach of the platform. And so this positive feedback system of reach and accelerated applications is one of the most vital things associated with vital characteristics of any computing platform. And so as you can see, the number of applications is starting to be accelerated, starting to increase. Our parallel speed up is of course great. Now the question is, what percentage of the workload do we represent? And accelerated computing, of course, responds and respects Amdahl's law. And so over time, one of the characteristics when we first started was the vast majority of these applications run on CPUs. And the long tail surely has a lot of applications that are not ported. However, application developers are clever. We focus on the highest workload percentages first. And accelerating one application after another, we're starting to now accelerate an entire data center. And whereas it used to be, a data center would start out being largely CPUs, with a few nodes or a small percentage of nodes being accelerated, increasingly you're going to see that a data center would be largely accelerated, and you would have some percentage of the nodes of CPU-only nodes so that you can continue to deliver throughput on the long tail. The benefit of accelerated computing is being felt everywhere. You could see that from the response of developers. Some 500 applications have been accelerated. 75% of the world's top 15 applications represent 70% of the world's supercomputing workloads have been accelerated. And so if you look at it from that chart, the vast majority of these applications that consume the vast majority of the workload of a data center has now been accelerated. We're really at the tipping point of accelerated computing. You know, I think all these numbers are interesting, but when you look at it, visually, it's actually just incredibly compelling. So this is what it looks like if you were building self-hosted servers, CPU servers, using the fastest CPUs available. 160 servers would be 96,000 watts, 96 kilowatts. And we would run, for example, the example that we're using here are some of the most important applications in high-performance computing. VASP, Amber, Milk for physics, deep learning, ResNet 50 is the example used here. Okay? And so these 4 racks of self-hosted servers, 160 servers, nearly 100,000 watts would look like this if it was accelerated. Look at that. Accelerated computing. 12 accelerated servers with 4 GPUs each, basically 48 voltas. 48 voltas does the work of this. 48 voltas does the work of that. The benefit of accelerated computing. Now the other reasons associated with reducing cost and power aren't necessarily intuitive. If you look at this, not only did we deliver the same amount of performance, we reduced the cost tremendously. We reduced the cost because the same data isn't copied across all of those 160 nodes. So all of the memory could be removed. The data doesn't have to be shared and synchronized across all of those nodes. As a result, the number of networking systems and connection fibers, the NICs, the top of rack NICs, the routers could be reduced. And as a result, of course, with fewer chips, you have a lot less space needed and a lot less power consumed. In fact, if you just think about the power consumed, my guess is that over the course of about 3 to 4 years, it would pay for itself, just in the power savings. And so GPU accelerated computing saves money. GPU accelerated computing reduces power. And because we represent so much of the workload now, GPU computing could be applied quite broadly. Now, one of the killer apps of HPC that we're starting to see is deep learning. And as you know, we do quite well in deep learning. This is some examples of the performance that we've been able to deliver over time. And if you look at this, this is one GPU, 128 Titan X's that we delivered in February of 17, was able to do ResNet training in 4.4 hours. So 128 GPUs train ResNet in 4.4 hours, literally February of 17. Shortly after that, Pascal P100 came out. Facebook was able to do it with 256 P100s and trained it for the first time, trained ResNet in an hour. What used to take, well, this is already incredible, but just a couple, 2-3 years ago, it used to take a whole week. Now we're able to train these deep neural nets literally in an hour. IBM announced shortly after, using the same architecture but with Power 9, that they were able to deliver ResNet 50 network in 48 minutes. And just a couple of days ago, Preferred Networks was able to do training of one of the most complex networks until just recently in 15 minutes. You could barely get up, make a cup of coffee. And the work that took literally weeks, and before that months, now takes 15 minutes. Unbelievable results. So deep learning has really been accelerated as a result of this. Well, what's going to happen here is that the network, of course, is getting more complicated. And these networks are going to be trained with more data. So the fact that we're able to drive training times down to 15 minutes is just an incredible achievement, but it's not to make it easier to do deep learning, it's so that we could do better in deep learning. And as you know, beyond this, we would like artificial intelligence networks to create other artificial intelligence networks. And so deep learning, AI will be running deep learning to create other networks for deep learning that they will train to be great deep learning networks. Deep learning has really come a long ways, and the results have been unbelievable and helping us solve some of the unsolvable problems. Now, deep learning is also coming to HPC. Let me explain this to you. As you know, HPC is about simulation. The most complex models, simulating problems that are either at the biological molecular scale, atomic scale, quantum scale, all the way to astronomic scales. Incredibly complicated things, either tons of them or huge ones. Very complicated simulations. And it's simulated in FP64 and FP32. And what I'm showing here is a GPU accelerated, a GPU accelerated supercomputer called Blue Waters. And this is usually what supercomputing will focus on. We built a supercomputer. You run a astrophysics simulation. It would take hours and hours or days and days, and you would get the results of it. The thing that's really exciting is this. We're starting to now take, researchers are now starting to take pre-recorded, previously observed data and use it as ground truth. Taking that previously observed ground truth, you can train a neural network with the ground truth and the simulation results. The simulation results would predict the type of scenarios and circumstances that we have never observed, but know exist. We have never observed, but know exist. And so when we know it's happening in nature. And so we would use the simulation to train a neural network that is labeled by ground truth and create a neural network, ultimately, to go detect these conditions. And so what I'm showing you here is the workflow of what you have to do. So you have to collect data, you simulate. Between the collected, observed data and the simulation, you would train a neural network. You would take all of the data you have and test that neural network to make sure that it works, that there's no regression. The things that you believe it should detect or predict, it does predict or detect. After you're done testing it, you can now apply this network to observe the universe, looking for that interesting phenomenon, that phenomenon you were simulating to discover. Now notice this. If you look at the formats, the precision, the mathematical precision necessary to do this, you start out with FP64 or FP32, depending on the type of simulation that you're doing. You train with FP32 and FP16. You do regression in FP16 or int8, and you inference in FP16 and int8. As a result, this particular workflow has driven, for the first time, multi-resolution computation, multi-precision computation. One singular computer in a supercomputing center will have to support all of these numerical formats in a first-class way. And this is the future, we believe, of supercomputers. The work that's being done all over the world in applying deep learning to supercomputing is just phenomenal. And the results that they're getting is not 10%, 20%, sometimes it's a factor of 100,000. Whether it's in particle physics, drug discovery, astrophysics, the results that the people are getting applying deep learning in combination with simulation is really staggering. All of these are blogged and written by us, and so I welcome you to go read more about them. We're also applying exactly the same approach to a field called artificial intelligence, AI cars, self-driving cars. The model that I explained earlier, we use exactly the same thing when we're designing our self-driving cars. 3D simulation for all the scenarios by which we either believe are too dangerous for us to go and try, we like not to try it, or it's very rare that that circumstance would exist. And we would create basically a photorealistic view of the world, and we would simulate ourselves and simulate this artificial intelligence car driving in this virtual reality world as we create all these different scenarios for it. We simulate. That simulation result allows us to try things, give our car experiences that it otherwise wouldn't have had naturally. Meanwhile, we have a data collection car we call BB-8. And BB-8 is out driving around the world, collecting data, trying the neural network. We would take that information, the data that's collected, observed data, just like the last time, the simulation data, and we would train our neural network. Our neural network then would have to go through a simulation pass to make sure that there are no regressions. And then after that, we would put the neural network in the car, running on a supercomputer in the car, we call Pegasus, that allows us to drive automatically. And that Pegasus car would detect everything around it, track everybody else's movement, figure out where you are relative to everybody, and plan what to do. A classically artificial intelligence problem, a robotics problem, and a supercomputing problem. This entire workflow needs to run on a supercomputer. And so Nvidia has built our own supercomputer, one of the fastest in the world, so that we could do this entire workflow, this modern workflow, this modern high-performance computing workflow inside our company. We called it SATURN V. SATURN V is powered by VOLTA, as you could possibly guess, 660 nodes. 660 nodes. Just 660 nodes. It took us practically no time to build it. 660 nodes, delivering almost 1 exaflops of deep learning performance. 660 petaflops of tensor ops so that we could apply it for deep learning. SATURN V, one of the fastest supercomputers in the world, super energy efficient, one of the greenest computers in the world, and we use it for our high performance computing software stack development. I think this is the future of supercomputing. This is the future of high performance computing, and I would argue this is also the future of software development altogether. It is only it's because of the work that we're doing in self-driving cars and all of the work we do in AI, the reason why Nvidia had to build its own supercomputer for the very first time. Until now, most of our software engineers coded on their laptop, they compiled it, and then ran regression tests in a data center. Now we have to have our own supercomputing infrastructure. I believe every single industry, every single company will eventually have to have high-performance computing infrastructures, opening up the opportunity for the HPC industry. The challenge of having no demos in the first 34 slides, there's no opportunity to breathe. I'm standing up here and I'm going, man, I hope Ryan's turn this soon. Speaking of Ryan, as I told you earlier, accelerated computing and high performance computing is all about software. To be able to pull together the entire stack of software on top of the architecture, all of the solvers and middleware and libraries, drivers, to pull all that stuff together so that it's functional is a miracle in itself. As you know, John Stone. It is just an incredibly great challenge. Not to mention that we want it to be optimal. Because in the final analysis, high performance computing is about performance. You're running a simulation job, you're running something that lasts days, if not weeks. You can't afford for that software stack not to be optimal. Not to mention, you've already purchased the system. You want to get the most out of it. And so you want that software stack to be optimized. Meanwhile, all of these layers are changing independently of each other. Each one of the GPUs have different versions of drivers. Each one of the versions of CUDA integrated into different solvers. Different solvers, of course, are backwards compatible, but which ones are optimized? And the solvers and the applications, they're all slipping and sliding against each other. And then, of course, we got to get a distributed computing going. And so that networking stack, that distributed computing stack we call NICL, all of it is incredibly complicated. The odds of it coming together is very, very low. And the odds of it staying optimized over time is practically zero. And so what we've done is we decided that we would dedicate ourselves to building every single stack. And we would optimize every single stack. And we would maintain every single stack and test every stack and do it for as long as we shall live. Which in my case will be a long time. And so this is a very large commitment. And so as a result, we take this entire stack, we virtualize it, we put it into this thing called the Nvidia Docker, NV Docker. We virtualize it, and we put it up into the Nvidia GPU Cloud registry. This registry only contains the software stack. It only contains the software stack. And once you log in, you'll find yourself a software stack, and you can download it, pull it down to any cloud, any data center that we've certified. And as I mentioned earlier, we're in every cloud. We're in every single server. We're in every single data center. So as a result, the power and the utility and the reach that NGC will give us and give all the developers and all the researchers is just going to be utterly incredible. But the most important thing is in the final analysis, it's got to be simple. And so with that, I'm going to introduce Ryan, who's going to give us a demo.
Absolutely.
Ryan, take it away.
Thanks, Jensen. All right, welcome to NGC. So the URL, so if you want to go there, ngc.nvidia.com. If you're new, sign up here. If not, go ahead and log in. And so we'll be conveniently reminded of what we're going to do in this demo at the front. So when you first log in, you're going to see 3 steps. And these are going to be your 3 steps to get started using our deep learning software stack. First, generate an API key. That's going to be your password when you take these containers out to other systems to be able, or that's going to be your password to be able to pull the containers down. Second, you're going to pick the software that you want. So you're going to copy your URL, bring it over to your computer, use that to pull the container. And then you're going to select where you want to run. So these are the steps we're going to do today.
1, 2, 3.
One, two, three. So when you land in the page, the first thing we're going to do, we're not going to forget, we're going to create our API key. We can't go anywhere without that. Jump in here, generate this key, and then copy it out. So that's going to be your password. I'll change it after. OK, so I have my password. Next, in this column, you see all the deep learning frameworks that we optimize. This is the work of some very talented engineers who do all the hard work so we don't have to. They package up Caffe, Facebook's Caffe 2, Amazon's MXNet,
Microsoft CNTK. And what we're going to be showing today is TensorFlow from Google. The amazing time machine called CUDA.
That's our base container. So actually, our base container, you can take and build any of your applications from our base container. What's really convenient about the registry is it's got a handy-dandy markdown page, so you can just read through, and these are the quick steps to get started with our frameworks. And so here, what we're going to do is we're going to copy our key. So this is going to be.
Now, meanwhile, while Ryan is doing, keep going for a second.
Oh.
While Ryan is doing this, so let me just tell you how this idea of doing all of this came about. We were doing deep learning all over our company, and deep learning engineers were building their own machines, because some of them were using Caffe, some of them were using PyTorch, some of them were using Theano, and so they were all building machines. They were all building these machines, and it turned out that amazing software engineers, it would take them a week, sometimes 2 weeks, just to build the machine, get all the software stack pulled together, get it all optimized, get it all working. Okay, all of the software is all over the world, spewed out all over the world, and you're going to go collect it all, and you're going to figure out a way to build it and make it work, make it all work, and get it performant. And so when we heard this, and we were trying to get, as you know, a self-driving car on the road, so I was rather, as you can imagine, impatient. And so when all of these hundreds of engineers are building these machines, we just said, hold on a second, guys, we've got to do something very different. Imagine if we're doing this, imagine the hundreds of thousands of artificial intelligence engineers all over the world, and what a huge waste of time. And how is it possible they're all going to have the patience to do this? How can we advance AI? How can we get everybody to jump on this bandwagon if just building the machine was such a challenge? And so we decided to do this. Ryan, take it away.
Yeah, I used to do this, and it was awful. And now it is, all I have to do is remember what month it is. And at the end there, 1710, that's the containers from last month. So it's that easy. So we're going to show you this on Amazon. So with the new VOLTA P3 instances on Amazon, so we can click through here, and it's going to give you some information on how to get started. And then you click this next button to go jump into your console. And so if you haven't signed up for AWS, you'll be asked to sign up. In this case, we're just going to sign in. Yep. Demos, live demos. Quick jump.
You need some money?
I could use a little help. Actually, so
it's $3 an hour. Use your own credit card. Watch, I'm going to get an expense report that says $3.
Yep. So I'm actually not going to show you exactly how to spin up an instance quite yet. Actually, I will. I will show you how to spin up an instance really quick. Let me just jump over and fix this.
Well, you could tell us what's happening.
I'm in a different browser window. So, We were looking at value props.
Hang on a second. But they made good ones. Yeah, yeah, sure, exactly. I mean, I believe in Amdahl's law. That's why it's a law.
Okay, so you log into your console, and in your console, you will launch your instance. Once you're in your instance, you go to the AWS Marketplace, and you search for Nvidia VOLTA. And you can select Nvidia VOLTA.
We should integrate this. It's so simple. We should integrate with Alexa. Just go, Alexa, I would like to train a network.
We have some internal people who have done that.
Yeah?
It's pretty
How
awesome.
hilarious would it be?
Yeah.
Yeah.
So when you get to this page, you can see the price breakdown. And as Jensen said, it's about $3 for a single GPU. It scales all the way up to 8 GPU nodes. And just click Continue. And then you'll select your instance type. And so you're going to look for the GPU compute instance type. And then again, here you see the options for the P3 instances. And then go ahead and click Review and Launch. This is the last page before you launch your instance. You have a chance to make a few edits on this page, so adding SSH keys or tags. Especially if you're spinning up a lot of containers, you may want to tag them. Or sorry, a lot of instances, you may want to tag them so it's easy to find them again in the future. At that point,
and that's a feature to encourage a lot of instances to be fired up.
Absolutely. So definitely go down and use this tag option. Absolutely. And then you can go ahead and launch the instance. I've already launched the instance, so it's right here, running, and I'll log in. Remember when I said you had to create an API key? When you log into the instance for the first time, you just have to paste your API key in here. So I'm just skipping that step because I'm already logged in. The next step is we're going to pull our container. And so that's as easy as doing a Docker pull. And I prepped this demo. It may not seem like it, but I have. So I pulled the container and got it ready to go. And now we're going to run the demo. So this is the commands to run the demo. So we're going to jump into our container with this NVIDIA Docker command. Now we're inside the container. And now we just change directories into where the example is. So we're just going to run the MNIST example, which is the Hello World to Deep Learning. And we're going to fire it up here. And that's how easy it is.
That's it, easy peasy. Thank you, Ryan. What an amazing demo. You know, we're a computer graphics company, so everybody expects our demos just to be shocking and amazing. And here we are, you know, after all these years, 25 years later, ASCII. One of the most amazing demos we've ever given. ASCII, running deep learning on a supercomputer in Amazon, in Oregon, the most advanced GPU ever created, the most advanced supercomputer ever created, running this entirely optimized software stack. And as we watched Ryan fumble through his computer, when he finally found the right browser, it was easy peasy 1, 2, 3, and there he goes. He just launched a training job, MXNet. Okay? All right, good job. And so that's it. That's the amazing thing about NGC Cloud, okay? And we're going to put everything up in the cloud. Now the other thing that we decided to do is we think that deep learning is not the only high performance computing stack that's hard. In fact, all of those scientific codes are hard, and they're incredibly hard. Whether they're molecular dynamics or computational biology or fluid simulations or weather simulations, all of these quantum chemistry, they're incredibly hard. They're just incredibly complicated. And the number of people in the world who knows how to build these stacks are relatively few, to the point where most people, once they get it up and running, they hardly ever get it tuned again. They're just so happy they got it functional. They're not even trying to make it fast, and they're not even trying to make it updated. And so we think that the right answer is for us to do essentially the same thing for high performance computing. And so today we're announcing that for as long as we shall live, that we will optimize, maintain, test these high performance computing stacks, and we will containerize it and put it in NGC. We're going to start with Games, GROMACS, LAMPS, NAMD, and Reliant. And Reliant, as you guys may know, is a reconstruction software for an instrument called the cryo-EM, cryogenic electron microscopy, which recently won the Nobel Prize for Chemistry. And Reliant is the computational software that goes along with this instrument that takes all of these electron scans and reconstructs it into a molecule that is in situ in its environment. Won the Nobel Prize. We're going to start with today these applications, and then we're just going to go at them one after another. Take all of these applications and containerize it. And then with that, we're going to do a quick demo. We're going to do it real fast in the right browser.
Yes, absolutely. So you may have noticed underneath the thing, it was live before, but now there it is. There's our HPC apps live. So just like you have our deep learning software stack, you've also got our HPC apps. The example I'm going to use here is NAMD. So NAMD is a molecular dynamics program coming out of the University of Illinois. So I copy my URL, and I'm going to jump in, this time into SATURN V. So SATURN V is our supercomputer that we have. I got a little bit of a very small, like carved out cluster of this, and this is what we're going to run. So you can see here, this is my demo script. As Jensen said, running supercomputer apps is a little bit difficult, so there's 3 steps. We're going to ask for one node of our supercomputer. Next, we're going to jump into the container. That's the NV run. I've wrapped the Nvidia Docker line so you don't have to see a super long line. And there's our container. There's our NAMD container right there next. And the next is the command that we're going to run in the stack. So let's go ahead and run that. And as we're launching it, it takes about 30 seconds to kind of load all 1 million atoms. So let's take a look. So we don't have to just do ASCII stuff today. We can actually look at the molecule. And this molecule is actually relatively famous. It's not a molecule, it's actually a virus. This is the satellite tobacco mosaic virus, or STMV. It's the first virus ever simulated atom-wise with molecular dynamics. And what's really interesting about that is this
Johnston.
Yeah?
No, take a picture.
Oh.
I'm sorry, inside joke.
The team at the University of Illinois actually would use like some of the world's biggest supercomputers, and they simulated this for half a year. And now what we're going to do today, we stopped the simulation, and we're going to connect, and we're going to live visualize that simulation that took a half a year on some of the world's biggest supercomputers, and we're going to start doing it right now. And the best part about visualizations is we're simulating everything, but we don't have to show everything. So we can jump in, and we can look at what's going on inside the virus and see all the interactions that are going live in the simulation. Oh, and by the way, because we can't move 1 million atoms over the internet, this OpenGL graphics is actually being done on a GPU that's sitting right next to the supercomputer, and we're only streaming the pixels back through VDI.
Amazing. Did you guys just see what happened? So here's his container. It's in the registry up in the cloud. He goes into this browser. He downloads it into a supercomputer. He launches the application. Not only can he run the application, because all of those that supercomputer's built with a whole bunch of GPUs. The GPUs would do the simulation, and it would do the rendering, and then it would compress it, and it would stream it, and send it over to his little Mac over there.
Yep.
Just like that. Easy peasy. And now the scientists could focus on science instead of building computers. This is just really terrific. Good job. Thank you. Okay, so I talked about NGC for deep learning, taking all those stacks and optimizing and maintaining it and testing it over time. We're going to do the same thing for scientific codes, high-performance computing codes. Equally complex, changing all the time. We're going to optimize it, we're going to test it, we're going to maintain it, and we're going to virtualize it, put it in the cloud, and you can download it and run it in any supercomputer. But there's more. It turns out that developing all the software is to gain insight, and nothing is more powerful to gain insight than to see it. This is methane and oxygen mixing together in a rocket. Not only is it beautiful, it's properly colored green. Just sit there and just watch it. It's mesmerizing. This one's also mesmerizing, but it's scary. This is the largest tornado, hit El Reno in Oklahoma, I think it's 2011. Look at the size of that tornado. We're simulating that, visualizing that, get a sense of its amazing majesty and incredible devastating powers. The power of visualization. However, there's so many different types of techniques to visualize. What Ryan showed you earlier was visualization used rasterization, OpenGL. You could also use ray tracing. Using ray tracing, you can see all the subtle shadows of all these molecules as they occlude each other. You could also use, in this case, volumetric rendering, because you don't want to just see the outside of the tornado. You want to understand the inside of the tornado, the fluid simulations in a volume. And so there's a whole bunch of different types of rendering technologies. Inside our company, we have 3 rendering pipelines. Ray tracing is called optics. Rasterization, of course, OpenGL, and engines that go on top of it. And a volumetric rendering system called Index. I'm so excited to tell you that this entire complicated software stack, that number 1, the technology doesn't exist inside a high-performance computing center. Number 2, to be able to take that entire accelerated computing graphics stack and put it inside a supercomputer, virtualizing it, rendering the data in situ, and then streaming it out. That software stack is incredibly complicated. What we've decided to do is take that entire software stack and containerize it. Put it into a container. We're going to do exactly the same thing that we did for deep learning, for high-performance computing. Now we're going to do it for visualization with all 3 modes of visualization. And we're connected to the most popular visualization system for high-performance computing called ParaView. And so now ParaView will be integrated with Index so that you could do volumetric rendering, huge scales, millions and millions of grids. You could do ParaView with optics, ray tracing, and generate these images that has all these subtle crevices and shadows so you can understand it better. ParaView with holodeck. What you were looking at just now, holodeck, in the future, you could render it, put your virtual reality goggles on, and stand in the middle of the tornado and imagine what it's like. Okay? And so these 3, ParaView with Index, ParaView with optics, ParaView with holodeck, will be integrated into high-performance computing software stacks inside these data centers, and most importantly, we're going to containerize it, virtualize it, put it up in the cloud. Let's take a look at it. Should we?
All right, thank you, Jensen. So basically, if I'm a scientist and I have my simulation running on a supercomputer, then I will typically use something like ParaView to visualize it. And usually it will look something like this. So this is a straightforward OpenGL rendering of the cloud coverage of a simulation of this season's storms that was done by ECMWF. And so if I just want to make this look good, if I need it for outreach or for teaching, then I will typically have to export it. I will have to run a different tool and spend a lot of time to get it to look good. And now that we've integrated ParaView with the holodeck engine, we can just flip a button, and we have the holodeck engine there offering its state-of-the-art visual effects on top of our simulation data. And so I can just navigate around.
And you can do all kinds of stuff with it, right? You could change the lighting condition if you like. You could add all kinds of textures. You could add all kinds of materials and all kinds of bumps. You know, you could render amazing things. Instead of basic OpenGL, now you have the state-of-the-art, everything featured modern computer graphics pipeline. Okay, let's take a look at another example. Now, meanwhile, before you guys start talking about this one, meanwhile, here's what's happening. There's a supercomputer in our data center, and it's doing the number crunching for that weather simulation. Then ParaView, which is distributed across all of those computing nodes, okay? Each one of the ParaView instances would then render its part, would collect up its data for its part, sends it to another ParaView server, which does the rendering. That ParaView server has has holodeck integrated into it. Holodeck is now in the data center doing all the rendering for all the data that's been collected into it, streamed into it. It does the rendering, compresses the images, and sent the pixels to your little notebook. And so as a result, we could do computer graphics of your data set from anywhere. It just doesn't matter where you are. Okay, so whether it was in the case of ParaView running holodeck, it could be ParaView running optics, It could be anything at all. This one is now ParaView running our index software stack, and it's a volumetric rendering of a nebula. Go ahead.
So thanks, Jensen. So what you're seeing here is our index volume rendering library integrated inside ParaView. And this particular data set was generated by Professor John Blondin. He's from NCSU, and this was part of the SciDec program. So they really wanted to understand the mechanics behind the core collapsing supernova. And this particular attribute we are visualizing is the entropy field of the supernova. So we took part of subset of the data and tried to do a time series of this. So you can see how the entropy field rotates around the core of the supernova star here. And the beauty of volume rendering is you can have really semi-transparent color maps and transfer functions, so you can look inside your data as well.
And
so
this is interactive?
Yeah, it's interactive, so I can move around, rotate.
It's not a movie, right?
No.
And this is what a star looks like. There's a little tiny core of a star in there.
Yeah. And the entropy field, you can see around the core of the star rotating in a spherical way.
Well, if we were an astrophysicist, we would understand this. If we were Stephen Jones over there, sitting over there, we would understand this. Okay. All right, you guys. Thank you very much. Good job. So that's our NGC announcement. What NGC is all about is a container registry in the cloud, and now these fully optimized stacks, fully integrated stacks, fully tested stacks, and we'll continue to maintain it over time. As technology continues to advance and change, we'll optimize it for deep learning, for HPC applications, and for HPC visualization. NGC in the cloud, registry of all of these optimizations, optimized software stacks. So, the time has come. In order for us to achieve and continue to extend beyond Moore's Law, as we seek the next major milestone in high-performance computing, exascale and beyond, accelerated computing, and its time has come. We're incredibly excited to say that VOLTA is in full production. VOLTA is in every cloud, available from every computer maker. The performance is incredible. We're incredibly proud of it. All of the software you're seeing today, all available for VOLTA. Deep learning is coming to HPC. I showed you a couple of examples where simulation and deep learning, simulation and artificial intelligence and data science can come together to create models and algorithms that otherwise are impossible to. We now have 500 accelerated applications, and these applications represent the vast majority of the heaviest workload part of data centers today. We want to make it simpler, easier for people to access these entire high-performance computing stacks and be able to take advantage of this fully optimized stack so that their data center utilization could be at its full potential. And then lastly, our GPU cloud for HPC Viz. For the very first time, fully accelerated rendering, fully accelerated computer graphics is now possible in high-performance computing data centers. And not only is it possible, we've made it easy by containerizing it and putting that on the NGC. It's really super to see all of you guys. This is the Supercomputing Conference. And this year, I can't be more proud of the achievements of this industry. Let's work hard so that we can help these scientists and researchers achieve the next generation of breakthroughs. Thank you very much.